Welcome to the third seminar in this term's colloquium. Before we start with the actual seminar, one piece of joyful news. We are delighted to announce that our DPhil students, Will Wolf, got the very prestigious scholarship, the doctoral scholarship from the Society, the British Society for Philosophy of Science. So congratulations, Will. Well done. And now it's our pleasure to have as today's speaker, Professor Renate Loll from Radbound University in Nijmegen. After receiving her PhD in theoretical physics from Imperial College in London in 1989, she spent several years inter alia at the Albert Einstein Institute for Gravitational Physics in Potsdam. She obtained her habilitation at the University of Potsdam in 1997 with a thesis on Wilson loop and discrete lattice methods in quantum gauge and gravitational theories. In 2001, she became professor of physics at the University of Utrecht, and since 2012 at the Radboud Universiteit Nijmegen. She's famous for being a co-founder of the nonperturbative approach to quantum gravity called Causal dynamical triangulations, a topic of substantial interest to philosophers because of its background independence and its vision of an emergent spacetime structure. I suppose we'll hear more about this in her upcoming lecture on questions on quantum gravity. Thank you very much, Professor Loll, for kindly accepting our invitation to come here today. The floor is yours.
Okay, thank you, Patrick, for this very friendly introduction, and I'm pleased to be here. Pleased to talk in front of a slightly unusual audience for my standards, and I hope I'll bring across some points on quantum gravity, and hopefully among them some you aren't yet aware of or are interested to learn about. So well, how did this come about? Well, Enrico, who is sitting here in the third row, approached me and said, "Oh, you've written this paper, the 30 questions." And I'm, inspired by that, he invited me, and I will address a subset of questions, but of course you're completely free, especially afterwards, to ask me anything beyond the sub-selection that I'm making today here. So let me get started. If I get, yes, here we go. So what is this going to be? So I'll give you a broad brush account of quantum gravity. So that's a field that I've spent most of my working life in, and I'll say something about past, present, future, and we'll also focus more on structural issues than on great technicalities, of which there are many, of course. So this paper I just mentioned is relatively recently posted on the arXiv, and it really came about from a summer school where I had to address a very mixed audience of PhD students, and I realized there is really no literature. I mean, of course, you find all Cambridge University Press books for the various individual approaches, but there is very little at an entry level and very little that shows kind of the broader scope, and also nothing that's very recent. So when a PhD student, joined me recently, I was actually at a loss what to give him for reading. So anyway, now I have something I can point them to. Okay, now various health warnings that come with this talk, and the subject in general. Of course, quantum gravity is not a settled theory, so that's to be kept in mind. In general, it's part of theoretical high energy physics, which one of course could characterize as a very subjective subject, a speculative subject. So the subject is fairly technical, but this talk will not be. So I'll try. Of course, you can ask me any also technical question or to fill you in on details if you like to. Also, it's just an hour, so I cannot do justice to everything that's been said and done in quantum gravity, but I will give you a perspective, which of course will also be in part my perspective, but it will not just be about my work, but trying to put it into a somewhat general setting. There are many different approaches, and given that as I always try and tell my students, there are no-go theorems, no-go theorems in quantum gravity. One should be, of course, careful to judge one or the other. And I try and stay clear of ideology in the sense of, well, this cannot possibly be right because these type of arguments, they tend to not lead at least to very fruitful discussions. So, but anyway, I think the way the field is going is in a promising direction where we are moving away from arguing about approaches and the beauties of our individual approaches and all the fantastic principles they adhere to, if only we knew what they were, to more concrete things where we actually will start computing numbers and comparing numbers, and on the basis of that start compare the theories and hopefully identify what the most promising direction is. Okay, now let's start with the simple stuff. So what is quantum gravity? In a simple definition, it is the fundamental theory underlying the classical theory of general relativity. So kind of our best theory of gravity. And it's, of course, kind of the one missing piece from our understanding of the four fundamental interactions. So which are, of course, all quantum theories in their very nature. So that's something we've learned from 20th century physics. But for gravity, we have not an understanding of what this underlying quantum theory is. So our ambition here is not just understand, but quantitatively lay down laws or whatever the appropriate way of understanding is that describes structure and dynamics of gravity and space-time. So that's, of course, the Einstein's duality on all scales, which includes the very small we are especially interested in. So where the so-called Planck scale, where we believe that quantum effects and quantum behavior really become of gravity really become important. So here's my favorite little hand-drawn line on a logarithmic scale, length scale, and just covering what we theoretical physicists are interested in describing, which goes all the way from 10 to the minus 35. That's the famous Planck scale, the characteristic scale of quantum gravity, to the size of the visible universe, 10 to the 24. So that's nothing but, if not ambitious. And you can ask yourself, so what role, roughly speaking, does gravity play in these various regimes? Well, of course, here, that's us. We are experiencing, of course, gravity in a very direct way. And it's curious that although this is also the force that was described theoretically first, right, by Newton a few hundred years ago, it's still, in a way, the least understood of the fundamental interactions. And, okay, here is, of course, the solar system. So we know, of course, applying Einstein's equations in a cosmological truncation seems to work very well, modulo the small things at 95% of the right-hand side we don't understand because it's dark matter and dark energy. Okay, but here everyone is happy. Then the realm of atomic, subatomic physics, right, that we can probe with particle accelerators. Well, there, gravity doesn't seem to play any role whatsoever. So why? Because gravity is so incredibly weak on short scales. I mean, relative, say, to electromagnetism, right? So many orders of magnitude, smaller. So it seems to be entirely unimportant. And of course, also not accessible to us. I mean, we don't have to include quantum gravity corrections when we compute scattering amplitudes, for the LHC. But then there's this magical scale where we believe the quantum effect will ultimately become important, and that's this very incredible, ridiculously small scale of 10 to the minus 35 meters. So that's a Planck scale. Now, does this mean this is forever completely out of reach? In any phenomenological sense that we might hope to make predictions with the theory of quantum gravity. I think, well, I would say everyone who works in quantum gravity, of course, believes in their heart that it should please be otherwise. So that we will be able, if only we understand what this is, to derive effects that maybe happen on very short scales, but could be enhanced. Could be there could be some other big scale, think of some astrophysical situation, something that's enhanced by inflation. What people discuss are dispersion relations, of light rays traveling basically to us since the beginning of the universe? Could they pick up interesting effects of a microscopic structure of space? And this is the kind of thing people are discussing. I would say probably if we are confining ourselves just to kind of effective field theory thinking, where we're just looking at H-bar effects in a kind of otherwise fairly standard, weak gravity setting, probably we're not getting to any predictions that are big enough to be seen in the foreseeable future. But we hope that looking at this from a non-perturbative point of view, this will suggest other things to look for, that to also work with the intrinsic quantum nature of gravity. Now, why are we interested in this? Well, here's just a range of the arguments good reasons that people do give, right? General relativity clearly is not valid on all scales and was never made to describe gravitational phenomena on all scales. So, I mean, one frequent goal is, of course, it predicts its own demise by predicting quite generically singularities in the evolution of the Einstein equations. And of course, close to those singularities, the equations stop making sense. So the question is, what should be taking over? Well, this should be maybe the laws of quantum gravity. And of course, very fundamental questions you can ask about the origin of space and time and of our universe. So how do we model that? Well, we are going back in time, right, closer and closer to the Big Bang. Of course, eventually, our classical description will not be adequate anymore. So then we hope that, again, quantum gravity will get us that little bit further into the past and provide maybe some explanation of why we see what we see on other scales. And of course, that's not the end. People ask fancy questions about, wormholes and time travel and what you frequently get in public talks. Is this possible, Professor? And then always, people of course point to quantum gravity as giving you possibly as a solution for that. So, let the quantum gravity person tell you what happens. Well, I think some of this is of course free fantasy, but this is just the way we explore the boundaries of our theory. So we are really pushing the boundaries by extrapolating also, of course, things that work elsewhere in physics on lower energy scales. And we hope that these tools will still be sufficient to tell us something interesting about the real world. Yeah? And the question is, how far can we push the methods? What are the correct methods for doing this? So what are other questions you could ask? Well, can I, we talk about early universe cosmology, can I point to kind of some quantum mechanisms by which this came about? Can I invent some, microscopic dynamics, quantum dynamics, or come up with some quantum dynamics from which those would emerge the structures we see? What we're thinking of is kind of, already quite early, some kind of de Sitter-like space with some kind of quantum fluctuations, which then kind of give rise to structure we see today. So can we really kind of quantitatively formulate some models that go really back to this deeper quantum regime? So is there a quantum gravitational origin of our structure formation? And of course, with the field is booming, right, since 2014-15, when the gravitational wave people came with the first signals from the detector. Everyone is talking about gravity. And I would say there is added pressure on theorists like myself to say, okay, can we come up with something, right, that these people might see of beyond Einstein gravity, maybe not with this generation of detectors, but maybe with the next generation of detectors. But it's a big question, but it has, I would say, energized also the debate, I think, within quantum gravity, more on the, let's say, result focused rather than, this endless arguing about, well, whose theory is most good. Anyway, so here we are. Why do we not have a quantum theory of gravity yet? Well, there are, of course, as many answers as there are people, but I think one of the key reasons is that, as opposed to the other interactions, spacetime itself is dynamical. And of course, you will always be familiar with this argument, right? For the other interactions, we are thinking of space-time as just a fixed background, an inert background that doesn't change no matter how crazily the matter behaves on it, we put on it, or the study. But that is, of course, different when we go to GR. There, space-time is the dynamical object of the theory. So, of course, and you don't know what space-time is until you have solved classical equations. You know, you've put in a matter distribution, you chose some boundary condition, then you solve these very difficult equations. Of course, in general, you cannot do this analytically, but you can try and solve them numerically, right? The people who study binaries, right, and whose gravitational wave signals we pick up, of course, they cannot analytically describe what happens during the in spiral because it's strong gravity is a highly nonlinear phenomena, but the numerics is extremely well developed, and this is how they can predict the waveforms that people then look for to interpret what they see in gravitational wave. Okay, now what am I saying here? Well, what I've already said is the Planck length is very small. Gravitational effects are very weak. If you saw in the NH bar, they become even weaker. So there's no very obvious phenomenology that is there that also we could use to guide our theory construction. So I think there is work, in this gap between what we can observe and what we theoretically understand. I think there is quite a bit of work to be done on the theory side to make our theories more complete. So the gap gets a bit closed from that side. Of course, the people working on the gravitational wave detectors, they're pushing their limits, and also people, of course, in astrophysics. So we have to work harder and come up with such predictions. We have to be better on the probabilities. If one wanted to look at the history of quantum gravity, of course, people started thinking about this right in the 1930s. People like Rosenfeld, etc. But I would say, and then thought about maybe perturbative. But then starting from the mid 70s, people, the first results by Tolfi, which I'm quoting, people understood probably that there was something wrong with them, of not being consistent at high energies with a perturbative description of the gravitational field. Perturbative standard quantum field theory, which of course makes use exactly of the split of a general Lorentzian metric G mu into a fixed Minkowski piece, which are called here eta mu, plus a small perturbation. Now, if you base your quantization on that, as you do standard and other quantum field theories, you find that there are kind of incurable divergences, or in more modern language, you pick up. Of course, you will always pick up divergences in these quantum field theories, but you cannot systematically remove them by renormalizing a finite number of coupling constants. So the theory in this formulation uses this predictive value. That was already kind of clear in the 70s, and people already believed that even before Gorak and Zaniotti in 1986 did this two-loop calculation in quantum gravity and showed it. So it's there. So the next period is, so if the perturbation theory is not the right way to go to find or construct a fundamental theory of quantum gravity, well, then where do we go? Then there is no unique route, you see, and then so from there starts a multiplication of ideas of how quantum gravity, first of all, what tools you should be using, and then how it should be kind of UV completed. So this is one of the kind of key ways of phrasing this. So and there are many, many possible roads that people could go down and did go down. Yeah? So that's a proliferation, the moment where this starts to proliferate. I'll say more about this later. Of course, another question you might ask is, going beyond perturbation theory, is the mathematics, kind of the old mathematics that of course underlies the foundations of a general relativity, is that still the adequate tool on the mathematical side? And of course, one could have one doubts that it is. Already, for people drawing pictures of space-time foam, and then you see all these spiky things, and then you ask, but there is no smooth G mu anywhere here. Yeah, indeed, there isn't. But somewhat schizophrenically, people insist on working with G mu and at the same time drawing these pictures, which are clearly seem to be in blatant contradiction with those. So I think the resolution is indeed you have to go beyond the confines of Riemannian or more problems with pseudo-Riemannian geometry to understand really what's going on perturbatively. Okay, let me not. So should gravity actually remain unquantized? Right? I think, I mean, physicists really don't believe that, generally speaking, because it doesn't really fit with what we have learned about nature. Everything being at its heart really a quantum theory and not a classical theory. But let me not comment on this further. Okay. Now, are gravity and quantum theory therefore then incompatible if we haven't managed for the last 90 years, depending on your counting, to do that? And that, of course, how the typical, so the first sentence on the typical popular article on quantum gravity starts, here is quantum gravity, we don't know what it is. No, here is quantum theory, it's all about the very small. And here is, gravity on the very big, and space-time is dynamical, and here time is fixed, and here time, we don't know what it is. So these clearly can't go together. Well, obviously, if we're working on quantum gravity, there's this belief, obviously, that they are not fundamentally incompatible, and I would say that turns out to be the case. So that's maybe not the best way of thinking about it. So what's the resolution? The resolution is to say everything's fine with standard quantum theory. Right? Of course, some people go out on a limb and they want to generalize quantum theory, but everything's fine with that. But you have to make sure that your quantum theory takes into account that space-time itself is dynamical. So that's the only thing in quotation mark, you have to do. And then you do find non-trivial injustices. And of course, that means also, well, one has to get away. So why is that a big step in physics? Because we are so wedded to this way of describing physics in terms of a fixed background. And also our Newtonian intuition is very much wedded to, X, Y, Z. Here I have a coordinate system, and here I set up my experiment. This is the way I understand physics. So it's a non-trivial, conceptual system. Now, classical GR, we know extremely well. And the point I want to make here is there are aspects of the classical theory that positively stand in the way of really thinking about quantum gravity. So let me point to some of those. So what underlies, right, the Riemannian geometry? So if you look at the famous 1854 habilitation thesis of Riemann's, where he laid down the foundations of GR, or of Riemannian geometry, he writes down the line element, ds squared equal to g mu of x, dx mu dx mu. Beautiful, super powerful. So the rest is, right, filling in the dots, comes GR, that has given us black holes, dynamical universes, what gravitation waves, what have you. So what makes it so powerful is the fact that, well, now in modern language, right, differential geometry. So you have these curved spaces, but you can put coordinate patches on them, and then you can compute as if you were on a real flat space, as if you were on, Rn. So that's very, very powerful, and everything is encoded into this metric tensor G mu. So this is what this is like textbook, or what we're teaching our students in the first GR course, right? The space-time is modeled on a smooth manifold, and we have coordinate charts. And then, okay, if you're interested in the curvature properties, then you compute this incredibly complex object with only 256 components that tells you everything about how space-time can be curved in all various directions. Okay, beautiful. But of course, it makes in a very strong sense use of the smoothness of this, the availability of tensor calculus. This is very, very powerful. And so it gives us, all of GR. What is problematic when it comes to the quantum theory? What is problematic is the coordinate charts, the choice of coordinates, because it introduces a redundancy from the point of view of the quantum theory. It introduces a redundancy in the theory, because you can describe one and the same geometry by choosing, you know, any type of different chart you like. And every time G mu will change its functional form. But you don't want to count these as distinct possibilities when you set up a quantum superposition, so a kind of finite path integral type. You only want to distinguish, I mean, you only want to superpose kind of physically distinct objects. Unfortunately, in the continuum, it is very tricky to remove the gauge degrees of freedom. I mean, so like gauge, I call it the gauge in analogy with, you know, electromagnetism, where of course we have local kind of gauge rotations or something like QCD. Yeah, that's gauge QCDs. So here we have this coordinate freedom or diffeomorphism invariance, and the distinction will not be material for what I'm saying. And already classically, one can of course be misled. You know, you can mistake something for physics, which in reality is just a coordinate effect. And there are, of course, very famous, from the early days of GR, famous examples that people were just confused. Is something a real effect, or is it just a coordinate effect? And that includes, you know, for instance, the event horizon of the black hole, or the status of the reality of gravitational waves. And of course, probably you know much more about these things and also historically than I do. But where even Einstein saw it, it's just fake. It's just a coordinate effect. Now, once it comes to the quantum theory, it's not just distinguishing, you know, physics and gauge, but is to systematically get rid of the gauge degrees of freedom is just immensely technically difficult, and there's all kinds of problems. So it really gets, if you stick with this type of continuum formulation, and that if you insist on the G mu, you always have this problem. And it's very tricky to handle. Okay, question number 5. Which choices are required a priori if we want to construct quantum gravity beyond perturbation theory? Now, message number 1 to get across, choices must be made. This is not always obvious, but you know, if you want to formulate some kind of dynamics, you have to tell me what your space of configurations is, and you have to make a choice of what your dynamical principle is, because otherwise you can't even start calculating. You know, there are people who say, okay, Feynman path integral, great. I just put in all possibilities there are, okay? And then that gives a wonderful quantum superposition of everything, and then magically all that I want, you know, from it will just emerge. That's just, of course, that doesn't work like this. You have to start with a well-defined, at least set of microscopic elementary degrees of freedom. That could be some field space, so that's just standard field theory. It could be some more general building blocks. You might fancy some discrete way about building up geometries. So it could be geometry, free geometry. It could not include or not include topological degrees of freedom, local topological degrees of freedom. You might think that, okay, maybe I shouldn't prejudice myself just by putting in, you know, any specific dimension, you know, but it should all emerge kind of dynamically. And maybe we should go beyond fields. And that's, of course, that was a big industry for 30 years. People saying, no, we should look at fundamental objects that are not local quantum fields, but they're extended objects. So the superstring theory or loops of loop quantum gravity. Yeah, so it's important to realize that goes beyond standard quantum field theory. And of course, these things, you know, they change over time. When I was a student before string theory came along, there was no one who ever questioned that the dimensionality should be 4. But of course, you know, the sense of what is natural, that changed and very much over the subsequent, you know, 20, 30 years. But of course, also now, actually, we do know more, because you, of course, you have to ask yourself, how do certain, you know, if you say you find dimensionalities are not 4, how do you get back to 4? How do you show in a concrete way that dynamically your system, you know, becomes 4-dimensional again? And then you are at a very hard technical problem. And if that's insoluble, well, you know, then what was the point of, you know, generalizing to arbitrary dimension in the first place? So there's some kind of correctives that do come in. So you have also to decide, in addition to the basic degree of freedom you're using, to formulate your theory and kind of what principles you want to adhere to your theory. And again, you must make some choices. There, of course, something you would never question if you were working on a fixed background, right? Things like locality, causality, unitarity, presence of time. But you might which you might question when it comes to a dynamical theory of gravity, where spacetime is not fixed a priori. Yeah? So people, at least verbally, are quite happy to just say, it's a Planck scale, none of this is there, no locality, no causality, it will all emerge. Yeah, that's wishful thinking for you. Then, of course, other fundamental principles that people like to adhere to, or because that's how they've been socialized in physics, right? This theory must be grand unified. So that's, of course, an extension of the gauge principle and symmetry principles, which were very successful in the 1970s, 1980s for us to understand gauge theory. Yes?
You didn't put background independence in that. Is that because it's
No,
obviously true it's not even a choice?
No. I mean, diffeomorphism, I would
okay.
It's very, very closely related to this. Okay. So, but so here the problem with abandoning these things, say at the Planck scale, is in how on earth do you retrieve them? Grand unified theory has now gone out of fashion again. I would say somewhat with the demise of string theory as a theory of quantum gravity. And it's, of course, it's question, many deep questions, but let's keep them maybe for the question session. Some people have a very deep belief, many in the quantum gravity community, that space and time must be discrete at fundamental levels. It's a little bit unclear where this intuition comes from, and I would also claim we don't have a very good intuition of what is this supposed to mean operationally, right? And we don't have very good Planck scale intuition, so it's I would say a mixture of wishful thinking, where certain things, it would be nice if certain things were finite. So if I supply you with a Planckian cutoff, then my entropy in some units will be a very large but finite number, right? So if I postulate, say it comes only in little, Planckian bits. I just it's an appealing idea that many physicists of the 20th century, I would say also when they became older, that things should be discrete because this is something that is more intuitive, to us. Counting things is more intuitive than the real line. It's not very okay. So fundamental symmetries I already mentioned. So do we put this in or maybe not? It's closely related to background independence. There are gauge symmetries. Do we have to blow up the theory? Do we have to include more degrees of freedom? Then it can come with more symmetries like supersymmetry, or even bigger symmetries. May other things like dualities play roles? Of course, that's very famous with ABS-CFT duality, gauge gravity duality. So certain choices will have to be made, and an important one is also the dynamical principle. And here is kind of one classic fork in the road. Do you do things the covariant way? So no 3+1 split, but you talk about spacetimes and closed path interval is epitomised with that, or you go for canonical quantization where you make some split, so space is kind of layered, and you have kind of space-time is just a sequence of kind of spatial images. And of course, in a technical sense, this will be some operator quantization. So this, although in simple examples like quantum mechanics, these are kind of equivalent ways of doing the same thing, say understanding the particles, the quantum dynamics of particles, right? I can devise a propagator from a Feynman superposition, and I can as well just get it from X heads and P heads and solve the Schrödinger equation. But these two things are equivalent. So they are presumably also equivalent in quantum gravity, but we know our understanding of the theory is so incomplete that going down these different branches, things then start looking extremely different, and it's very difficult to understand how they might ever be related again. But that shows you, I think, more about the incompleteness of our understanding. Oh, okay, that is the question. So is quantum gravity if we don't have access to, measuring things on the Planck scale, if even our best particle accelerators are still 16 orders of magnitude, in resolution away from the true Planck scale, does it mean anything goes? And the answer is fortunately no. So that's a little bit of positive news. So there are things we have learned. So it's not just, waving my hand and it should be like this or it shouldn't. I would claim, and from the statistics, you have most choices of microscopic ingredients which you might use just, to cook up what you think is what spacetime should look like at the Planck scale with whatever prejudices or mathematical capabilities you have for putting together. But most choices, but they will not lead anywhere. Because, well, you can play around with these systems, but you will have difficulty relating even to something that looks vaguely like gravity or spacetime. So they're not even wrong, using this old adage. Now, one hard criterion for quantum gravity theories is that if you give me one, and then if I look at it at large scales, kind of if I zoom out from these Planckian scales, eventually things must match with what we know to be the correct description of gravitational phenomena at macroscopic scales. And this is just Einstein's theory. So that's the hard criterion of the correct classical limit. Unfortunately, in non-perturbative approaches where you abandon, especially where you abandon kind of G mu at some early stage, you have tremendous difficulty in getting back there. Yeah. So it then becomes an intrinsic difficulty, and typically you don't even have the computational capabilities to determine what is, to test whether this classical limit is there or not. So then again, you don't really know where you are, where your probability series stands. So as I have already mentioned, this idea of emergence, starting from some primordial soup of some little Planckian building blocks, stirring well, and boop, emerges beautiful space-times with all the properties we know from the classical theory. It just doesn't work like this. So, because, well, why am I saying this? Well, people for 30, 40 years have actually worked with very concrete models in a more mathematical sense. I have studied them with computer simulations. And what one finds is that there are some very generic effects, to start with, which are called entropic effects, that make these systems degenerate, of your little building blocks in very characteristic ways that unfortunately interfere with the emergence, say, of an extended four-dimensional structure in the first place. So, and this is generic. Yeah. So, to give you a flavor, so you have your little building blocks, right, and you put them even in a kind of a path interval, but generically, so in 2 dimensions, where this whole game started, in what is now called random geometry. So I'm talking about, which something I could characterize as statistical models of, if you like, little elementary building blocks that interact according to a very simple principle, which is just the superposition principle encapsulated by the finite path interval. And then you take, you sum over all the possibilities. So you look at this big quantum superposition and then see what you get, basically. So it's very, very elementary ingredients and nothing exotic. So no way to go terribly wrong. So this game started in 2 dimensions back in the mid-80s when people were interested in understanding the dynamics of worldsheets of string theory. So in those days, these were the early days of string theory, and people wanted to understand it beyond perturbation theory, the same what we want to do with gravity. And of course, the worldsheets have a certain geometry, and that's in a way, that's what you're interested in. But it's difficult to understand. How do you go beyond perturbation theory, having them as nice, smooth classical things with some little wiggles? Well, people triangulated them, you see? And this is the birth of random geometry. It ended for string theory at the moment when people using these methods, amongst other things, understood that bosonic string theory is actually not is not consistent because it has tachyons, so negative energy excitations. But nevertheless, a methodology was kind of born, you would say, just to describe systems of dynamical geometry. And although it didn't lead to string theory, it led to absolutely beautiful, exactly solvable models of quantum geometry in 2 dimensions. So you could say these are toy models of quantum gravity, but what they showed you is that the methodology is sound in the sense that you get something non-trivial, which you can treat as a statistical model. This has a certain, behavior. You can take a large n limit, and outcomes a structure that nowadays goes by the name of. It's big. It's a big branch of pure mathematics these days, associated with notion of it was called dynamical triangulation in the old days. Associated Liouville gravity is another way, and random geometry as a subject, mathematical subject, is really a big thing. It's a big story in pure mathematics. So this is where it originated, and it tells you there's something rather than nothing. But unfortunately, well, you can try to apply the same things in higher dimensions, but then you meet some of these generic behaviors that interfere with emergence of macroscopic geometry, classical geometry.
Very quickly, just to clarify, in these statistical models, do you allow interference, or are you thinking of a Euclidean kind of?
Yeah, I get to this. They were, of course, all Euclidean. They were Euclidean, but of course, if you have a well-defined Wick rotation, these two things are equivalent. Yeah. So it's just a certain quantities that you're trying to compute. You're unable to do it in a certain part of the complex plane, but then you compute it by analytical continuation. So I would say there's nothing very deep in there, but these people were completely happy to stick to pure Euclidean language. So they never asked these questions. So how would I actually rotate these results back? And they're still not asking them. But what I'm pointing out here is there is a rich class of 2-dimensional models of dynamical geometry. There is a well-defined branch of mathematics where one now understands the properties of these ensembles in a continuum limit. And for instance, what comes out here is something that people call the Brownian sphere. So the language already, it tells you there's an analogy with 1-dimensional random objects. Yeah, random paths. Yeah, which describe, for instance, 1-dimensional quantum mechanics. But the property of random paths is right that they also have a non-trivial continuum limit. Yeah, it's described by the Wiener measure, and so this limit has also certain properties. Yeah, and some of them are kind of classical, but some of them are extremely quantum because these paths are kind of nowhere differentiable. The paths that give you something like the Wiener measure are nowhere differentiable. And you should think of this as a typical object that you find when you study 2-dimensional random geometries, where it's not constructed from little edges that form random paths, but 2-dimensional objects that are formed from little random gluings of little triangles. So this is what you're getting. And it's an object that is kind of also nowhere differentiable. So very, very spiky as the individual objects, but this is what quantum geometry generically will look like. In higher dimensions, unfortunately, it will not only look like this, but worse. For instance, it will tend to degenerate into what we call branch polymers. So the a priori also counterintuitive findings that I give you 4-dimensional little building blocks. So I play the same game. I play for random paths and random surfaces in 4 dimensions. So I just get little 4-dimensional building blocks. I glue them together. How could I possibly get anything that's not 4-dimensional? Well, it's these entropic effects that even these microscopic building blocks, even if they're 4 dimensions, they preferentially align themselves, say, to 1-dimensional branching filaments. And then you get something that has absolutely nothing to do with an extended geometry. So unfortunately, that's why I said it's one specific answer to the question, okay, I think of something at the Planck scale. Well, obviously, interesting physics will come out. I would say 99.9% of cases, absolutely nothing interesting will happen. Okay, here we come to switch to a little bit of historic, how, in what order are things happening? How is this to be put in context, which I think is also interesting, particularly for this audience. So I'm starting from the moment of it is understood, perturbation theory is not enough. What do we do next? Do we go down the non-perturbative covariant branch or the non-perturbative canonical branch? So here we stick, I mean, broadly speaking, kind of this G news, I mean, for space-time quantities. And here we have a split. We introduce spatial surfaces, and associated with every surface there, there are spatial metrics and their conjugate momenta. Yeah, something like coordinates and velocities on your configuration space. So here, what are the various approaches that people have looked at? Well, lattice quantum gravity, kind of in analogy to putting like QCD on the lattice, quantum Radbound calculus, which I'll say, well, let's say a little bit more about Radbound calculus. Euclidean quantum gravity, that's the Euclidean path integral, very much propagated starting in the 1970s by our colleagues in Cambridge talking about. And then, I mean, of course, a big boom now in the, for the unified dynamical principle superstring theory, 1984 and later. Was much richer than just a gene. So a lot of extra stuff here. But what is the essential thing? One tries to solve the path integral in one form or other. So that's a covariant way of doing things beyond perturbations here. Now here the canonical thing, as I already said, things look quite different. Well, people did study the canonical quantum gravity in a metric formulation, kind of using these variables. Then in the late 1980s, alternative classical variables were suggested. So these were the Ashtoka variables, which looked more like Yang-Mills type variable. And from there, a new canonical quantization program emerged by the name of the quantum gravity. What is the essence here? Well, you solve what is the quantum dynamic equation is the Wheeler-DeWitt equation. So this is a so-called Hamiltonian constraint, certain operators that you apply on wave functions, and that projects out some kind of physical configuration space. This is very difficult. Okay? So, well, maybe there's some conservational difficulties, but again, things do look very different in these two approaches. And yeah, so, but focusing on the common issues, one could say, with some hindsight, maybe also. So, what are common problems that you find no matter what approach you're choosing? Well, how to go non-perturbative and how to do any computations in a non-perturbative setting. And then that comes back to the point I made earlier. I mean, how do you the regularization methods? I mean, getting rid of the infinities, how do you do this in a way that doesn't mess with the symmetries of your theory? So that's a very, I would say, you could say it's a technical point, but it becomes so, the difficulties in some points are so overwhelming that you're wondering whether you're going down the right route. Okay. So that gives me an entry to say, okay, let's maybe look at the quantum gravity problem the opposite way. Let me think of what I have in my toolbox and how I'm understanding now with the best of what we can do in theoretical physics. What can I hope for in the best of all worlds? What is a realistic but maybe positive way of where to make progress? So what is the ultimate form my theory of quantum gravity could take? Now, I mentioned already, right? I reminded you of the Riemann tensor and its many components. It's just to give you a flavor of what intricate local geometry the Einstein equations describe. And of course, the Einstein equations are not exactly simple. It's just a set of nonlinear coupled partial differential equations. So here we are talking about being ambitious in wanting to find a quantum theory of some strongly interacting quantum fields with a very, very, very non-trivial field content and symmetry structure. So the diffeomorphisms. So if you look around elsewhere in physics, what have you been able to do so far with theories that are in a way much simpler than gravity? Well, basically, if if you're asking for something like analytic solubility, the only examples there are really in 2 dimensions, 2 space-time dimensions. Thinking in statistic models, using model, or conformal field theory, and things where you have large numbers of quantities. Algebraic quantum field theory cannot produce any examples apart from a few 2-dimensional models, integral systems, matrix models, tensor network models. So in 2 dimensions, also systems have there are many ways to solve if things analytically things go well. But if you ask, so which of those solution methods generalize to higher dimensions, the answer is none of the above, typically. So what can we do if we really imagine we want to describe a strongly coupled quantum fluctuating Planckian dynamics? We don't expect that we will be able to find R kappa lambda mu nu hat a direct quantum analog of the Riemann tensor. This is just out of the question. You cannot, you're in a setting where you probably have not access to something like tensor calculus. So what do people do? Well, you say, okay, either you really have to take this structure seriously and non-perturbative, or alternatively, maybe if you're lucky, there's a magic wand. And the magic wand could be something like a CFT duality if it would work the following way, that you have a weakly coupled gauge theory, and that allows you to understand a strongly coupled gravity, thing on the gravity side. That's the region we're interested in. The current status of the gauge gravity duality is the opposite. So we're talking about strongly coupled conformal gauge theories on the boundary, and they are dual if you use a conductor to something that's weakly coupled in terms of gravity. So that's not the interesting thing we are after. But I'm just saying, in terms of what you could hope for, if you come up with some other magic wand, by that I mean something that by which you can avoid really tackling that non-perturbative regime. Because my claim would be, if you really directly tackle that non-perturbative regime, there's just no other way than using computational methods to understand what's going on, because it's the same as you condense Smaller models, or something like QCD in the non-perturbative. So you need, how do you get hold of quantum gravity there? Well, we really, we want to understand this non-perturbative, the content, and how do you do it? So how do you come up with what I call the reality checks? Well, you really need to rely on numerical tools. And I mean, over the last 20, 25 years, we have learned of some ways of how to do it. So I just want to highlight the 2 main developed ones. So one is Markov chain on the power simulation. So that's really very analogous to what one does in, say, non-perturbative lattice, the QCD, which is very, very powerful because, for instance, in lattice QCD, you can now compute, the spectra, particle excitations spectra, just numerically, which is totally out of the question, of course, analytically. So you get very physical non-triviality. So in this category 4, something like lattice gravity, dynamical triangulations, or CDT, that's my variant. And on the other hand, that's been very much studied by people also coming from quantum field theory, functional renormalization methods. So which have some non-perturbative flavor where you compute flows of coupling constants as a function of scale. So in the key, I won't have time today to say anything about this. So this is the whole asymptotic safety approach. I think it's interesting, it's potentially powerful, but it also needs to make some assumptions, introduce some cutoffs in making the choice of which terms you let flow, and which making a choice of which coupling constants you include in the equation. It's very difficult to understand how valid this choice is within the same methodology. I would say this has been, this need here to rely on numerical tools has been an extremely hard sell in the community, especially people coming from a GR background, although I would say those should know much better, because yeah, as I mentioned at the beginning, we need numerical methods even to understand what the Einstein equations predict in strong gravity situations. And it's even more true, I would argue, in quantum situations. This is changing very slowly. So I don't know. How am I doing this time? Okay, I'm at Q9. Here is my next historical slide. So you remember, of course, your perfect memory, my previous slide with the two branches. So here I pick up on this, covariant quantum gravity and canonical quantum gravity, but now looking at what happened since the year 2000. So this is my year 2000 line. So remember, this is superstring theory. Here's loop quantum gravity. So both kind of very different, but curiously both, formulated from the postulate of finite extended objects as elementary excitations. Here, well, the uniqueness. I mean, there's a many free parameters, I would say, have really built this as a fundamental theory of quantum gravity. And people 20 years ago stopped calling it this. So therefore, for so many things, understanding the quark-gluon plasma, understanding cosmology, understanding basically everything there is, but it's not because of the many free parameters. It doesn't seem to be a natural choice for a predictive quantum gravity. Okay? So it's a strings as a framework. This is how people talk about it these days. What has happened on the loop quantum gravity side? Well, I would say one really ran into some intractable problems, and they're still not solved. It's a really good equation. It's an algebra of constraints. How do we faithfully represent the quantum theory? And this boils down to the question: how do we handle diffeomorphism symmetry correctly in those theory? I would say these are ununderstood things, and they are so hard that one should wonder, what is this the right way to go? But some people keep at it, and that's good. That's good. People here have branched into, they're still doing loop quantum gravity, but they've branched into applying it to reduced settings. So quantum cosmology is one of them. We just have pick out frequent factor with type variables. Black holes is another one where you start already in a setting that describes some kind of spherically symmetric black hole kind of background, and then you build your quantum theory using some of the principles of quantum gravity. So let me not talk anymore about the canonical side, because also really, I would claim the bulk of the community has now gone covariant again. So there is not so much, apart from this corner here, there's not so much going on here. And there has been a general revival of what I would call good old quantum field theory. So the embarrassment of riches of this extended formulation, string theory in particular, is of course not only you have strings, you need for consistency, you need to introduce square dimensional objects. So, and then that's then where you're picking up all these different vacua, different big parameter space. So this has become very much the story of the day. ADS-CFT's gravity duality, holography is a new organizing principle, and in more recent times, kind of to me, very amusing revival of the two-dimensional Euclidean path integral. So that's kind of the stuff that was abandoned 40 years ago, but here it is again. On the other hand, the more interesting part is also in 4 dimensions, is kind of what we call lattice gravity below. So the way the dynamical triangulations are just going to correctly doing it the causal way, introducing the Lorentz structure and this asymptotic safety code that I have already mentioned. Okay, so the other, also part of these people have migrated into spin foam models. So there's kind of an analog of quantum gravity. There's quantum gravity concepts, quantum information, people playing around with quantum bits in the hope of emergence. I'm not going to talk, so these are lots of stories that are interesting in research, but I won't talk about it. I'm always out of time anyway. I'm not talking about this. I want to zoom in a little bit on the causal dynamics. So where are we going? Well, we are learning over these decades how to accommodate dynamical geometry in normal QFT, so no extra, no exotics. This raises not just technical but also conceptual issues. For instance, also having to do, of course, with the epsilon fixed background. What do you mean by scale? So if you apply renormalization group ideas, and normally there's some scale that tells you, okay, on 1 meter it behaves like that. If I coarse-grain to 2 meters, it's that other thing. If I don't have a fixed scale, where do I even start talking about scale dependence and renormalization? And general statement that I just very, very deeply believe in. Approaches amenable to numerals have a huge advantage over everything else, and they will be what's there in the end. So I'm not so sure. Now I have a little bit on the lattice story, CDT. Shall I wrap this up? It's a kind of 3 more questions, and then it's the outlook.
Brilliant, next slide.
Okay. What is lattice quantum gravity? Well, putting gravity on the lattice. Unfortunately, yeah, it doesn't work for gravity. So, but let's recap. So what's the idea, which we borrow from our successful colleagues in theoretical high energy, working on QCD standard model? At the lattice, you model spacetime as a lattice, it acts as a regulator, because the lattice edges, they have some finite size. I put my fields here, and there's a finite number of points, and all my path integrals and whatever I want to calculate, it's just computed, it's just finite integrals. That if things are well done, if they converge, then I look for interesting things to happen in an A equal to 0 limit, where I let link individual things and kind of keeping the physical size of this lattice the same, but making the individual building blocks, kind of shrinking them away, and look for universal properties that remain, that are not actually dependent on the details of how I set this. Okay, beautiful idea. Can you apply it to quantum gravity? Well, people starting in the 1980s, late 70s, try to do this. The best way to look at most similar gauge theory is to use the so-called first order formulation of gravity, which is classically equivalent. Instead of G mu nu, use sphere bind and a connection. It's a bit technical, but so people just did this, like put it on the lattice and see what they get. All right, that's fine. And do Monte Carlo simulation. Unfortunately, they never saw anything interesting at all. And it's a long story, but so what one can point to as at least one likely reason is, well, if I just put my G mu nus or my field-bound was on the lattice, I'm totally ignoring the classical diffeomorphism. It's just very bad, it's so badly broken that you don't even know where it went. Yeah. So okay, so maybe that's the reason why we never saw anything interesting. And also what stands in the way, one should say, as a technical thing, these simulations, they have to be run, well, in a Euclidean domain. So you cannot do this. This was what Enrico asked me for. You cannot do the complex superposition, but you have to kind of rotate to the domain. And unfortunately, the Einstein action has this nasty property of being unbounded below. So even if you just say, okay, I just do Euclidean gravity, just throw it on the lattice, then the whole system is going to, because you have something that's called a conformal divergence. Now, this is all stuff, more or less simultaneously. There was a less naive and clever way of thinking of putting gravity on the lattice, and this turns out to be the right way. And it's based on the beautiful idea of Regis from 1961, of doing classical GR. That was his incentive, without ever introducing coordinates, to try and solve the classical equation. So, and it turns out when you apply this in the quantum theory, it solves this overcounting problem due to the diffuse. So this is really a very important point, but take it away and ask me more in the question session if you want to know more. So what's the idea of Regis? Well, here's the without coordinates. He approximates space-times, curved space, by doing together flat building blocks. It's like the two-dimensional flat triangles. I recommended you to solve string theory. Here's a four-dimensional analog, but this came really from trying to solve the Einstein equations away from situations of symmetry, because that's the only situation where we can solve these equations typically. But what do I do away from those? So that is suggested to do this, to discretize, and you're not discretizing space, but you're discretizing the curvature. So space is still continuous, but it's not a nice and smooth thing. It's piecewise flat. So instead of G news, the variables you have are the edge lengths of these things and the gluing data of how you assemble these to get curved spacetimes. The beauty being that this is a much easier data space to handle. Yeah? And that's also the reason why people in the movie industry, triangulate their figures. They don't work with GNUs, but they triangulate shapes and surfaces, to make them easier, accessible to computation. So the beauty is, again, that simply no coordinates need, you do not ever need to introduce any coordinates. When you compute with these things in the computer, the only thing you, of course, you need to do is you need to label these things, because you need to know, okay, this was, this is one is called number 1, and the building blocks next to it is called number 8. And in my big matrix where I keep the gluing data, I have to tell it 1 is glued to 8 and 8 is glued to 15, etc. So I need to call them, give them names, but it turns out that this redundancy is extremely easy to get rid of and take it. So the full power of this, I would say, it's been tried in the classical theory. It's not super powerful compared to other numerical ways of doing a classical GR, but as a true power, it's really unusable policy. And it has to do with the fact that really you don't have to take care. And if you look at the set of all distinct objects you can glue from these elementary building blocks, there is no further gauge redundancy, at least the way we do it in DT and CBT. Okay? So the implementation in DT would be to say, not like Reggie did, we allow all these edge lengths to vary individually, but all is the same edge lengths. So the entire dynamics is in the gluing. And that's the same thing we do in CBT, but our building blocks are Minkowskian and they're not Euclidean. Okay. So this is all very broad brush, as I said on my first slide. So what's the way to think about CBT? Well, it's nonperturbative, backward independent lattice formulation, which addresses all problematic features of the nonperturbative path integral in a concrete way. So people write down this path integral and say, this is quantum gravity, but this is like the most ill-defined object, basically. Because writing this down, you don't know what this is, you don't know what this is, you don't know what this is, and you don't know how to do it. Okay, so what is a way to define the path integral properly, to tell you what each one of these elements is precisely, and know a way of how to do this kind of for finite dimensional, for finite set building blocks, and then take a limit as you shrink the building blocks to 0. And this is not a well-defined definition. If this thing is for all finite triangulations is a well-defined thing. Now, of course, you have to make sure it is. You have to choose it. How can consider whether it is. But so this is the main idea of CBT. So really, a very specific description. This is quantum gravity. Of course, the final result, the ingredients are very simple. But of course, the dynamics of how these individual histories they interact with each other, that dynamics is not simple at all. It's like a strongly coupled system, right? And we have to adjust our expectation of what kind of quantities we'll be able to extract from this. But it's very first over all the environment. And well, we can really use the Monte Carlo methods to evaluate it. There's a big rotation behind this. And it takes care of these nasty degeneracy problems. So there seems to be a nice phase that extended geometry comes out. So I'm very curious. Now, what is key here? So what's different between the previous Euclidean path integrals structurally? Well, the gluing rules for the building blocks, so of course the building blocks are Minkowski, not Euclidean, but the gluing rules are such that we're saying they can only be glued such that kind of the light comes all point in the same direction. No? So, and there is something that is a time. Of course, time is not unique, but when you do this, it turns out you get a totally different model with totally different properties. If you now look at what does become this path integral in this continuum limit, you get totally different results. Already in 2D, you get an inequivalent result, And in higher D, where the Euclidean masses didn't really lead you anywhere, you see beautiful things happening. And one of them is the appearance of an extended geometry. So that's what this is about. So in CDT in 4 dimensions, there is strong evidence, so that's the quantum geometry. So that's our name for what comes out of this Feynman superposition of the path integral, has interesting properties. And some of those properties, there are some few properties of this we can measure and understand. And some of these have a nice classical interpretation. So we can measure, number one, dimensionality, characterizing kind of house of dimension and spectral dimension. And we find that macroscopically this is 4. And that's not a given, because typically these things degenerate to structures that have other dimensions. They can have very large dimensions, they can be infinite dimensional, or like these branch polymers, they can be 1.45 dimensional. So this is not a given. Moreover, we are able to monitor the size. So that's a very rough characterization of the geometry. We have a natural cosmological time, and as a function of that time, we can monitor in the sense of expectation value the volume it has at a given time. And this turns out to have a certain shape, so that's a Monte Carlo snapshot. So it starts at 0 volume, it becomes something bigger, there's some fluctuations, and it becomes small again. And when we looked at the statistic and measured all these curves in the center of expectation, we could beautifully map it onto the volume shape of the universe. So that's the classical solution. The answer, in fact, is a very simple line element. But here, of course, when you write this down, you have put in that it's homogeneous and isotropic, etc. What is a fascinating thing here? We've kind of we have found a space-time which, at least with respect to 2 properties, dimensionality and this shape, reproduces what we know from A solutions to the classical Einstein. It doesn't mean that this is the Sitter space, and we know already it's extremely quantum fluctuating. So there's more needed to ascertain more of these properties. But this is another talk. So I will skip this. It's just telling us how something can be not 4-dimensional, but this is generic in these random geometric systems. So let me jump to the last slide. It goes basically, we say, summarizing some of the points that I commented on during my talk, but now being phrased in a forward-looking way. So not all of those, you can ask me about them, will be immediately obvious, as that's where we should be going. So my way of thinking about quantum gravity and, say, the CDT approach in particular is really as a kind of a minimal non-perturbative quantum extension of GR. So there is no frills, there is no new principles, that are being involved. So, and the way I look at it is this is not a numerical approach to quantum gravity. That's the wrong way of thinking about it. It is computer-assisted theory construction, because you have a strongly coupled system. You have a precise prescription where it came from. So it's just the path integral, which you have, in a regularized form, you have given a well-defined definition, and then you take a continuum of it. But it's very difficult to analytically describe the final result. So we have to think about how do we describe it, and we describe it currently with looking at observables, non-perturbative observables. So each observable is a diffeomorphism invariant question we ask to whatever our computer is generating, and this is how we understand, we get an idea of what this is. So so we're getting insights like the dimension of this thing can be something totally unexpected. And before one studied these systems, people were naturally assuming that nothing would ever shake the 4-dimensionality if you use 4-dimensional building blocks. I mean, we don't even get to that idea, but this is just how these tools expand your horizon and your idea of what the theory could be about. So what is an important point to emphasize, also to practitioners of other approaches, what I call expectation management. So again, what might we be able to say, given the tools that we have, at our disposal in theoretical high energy physics and mathematical tools of what quantum gravity can be and deliver in such a strongly coupled regime? Yeah, So observables are one thing, looking for universal properties. So it's going away, if you like, from exact equations to the way we are thinking about complex systems. Is more, if people talk about emergence, you see already it's putting an emphasis on the process. So what is the process? We're looking at certain geometric observers and we try and understand how they behave under a change of scale. And that gives us some idea of what this theory is. Of course, we match it to the classical thing, that's fine. But this is more about what shape does the theory have and what can we expect to be able to know and in what mathematical form. There is something rather than nothing. So there is a rich, very explored dynamics and related to what I would call, beyond Riemannian mathematics. And what is a very interesting point is that in mathematics, people from totally different motivations have started to look beyond Riemann curvatures. What is geometry? How can I characterize the geometry of a general metric space that is not smooth? And how, for instance, can I define the notion of curvature, Ricci curvature? So this is our new big game in CDTs in between years. We have a notion of quantum Ricci curvature that can be evaluated on these totally spiky geometries. And the idea comes from pure math. So there's a mathematician in discrete mathematics called Olivier who invented a Ricci notion of Ricci curvature, and we've adapted to quantum gravity. So I just want to say there is there's stuff going on in mathematics. There's stuff going on in GR, in mathematical relativity, where people start looking at what they call low regularity classical GR, where you no longer require everything to be, C infinity or even C2, but you try and understand what survives of the equations, of causal hierarchies when we lower regularity. And it goes in this way. So there is, interestingly, things in math and physics, kind of new ideas that have been going on in parallel. But I would say, and also with the random geometry aspects, that are kind of coming together. And it's the new mathematics that we need to understand quantum gravity. So we have a blueprint for the emergence of quantum spacetime from first principle. I think that's beautiful. If other are not wedded to CDT, if other approaches come that have computational capabilities and that can compute them, they can do the same observables. So we are asking questions here which we can ask because we have a very concrete setting and which are very structural and probably are very relevant for any theory of quantum gravity. So that's my general philosophy there. And what I see also, and what makes me very happy, I see a kind of clear-cut path to what to do to relate this to a universe phenomenology. So we have already a quantum. I briefly sketch what we do. So we have this de Sitter-shaped object. It's four-dimensional. We have, with this new quantum Ricci curvature, we have satisfied and verified that the average curvature, so as a function of sphere, this is quantum Ricci curvature that would take me too long to explain, matches also that of a classical de Sitter space. What we cannot yet do is to understand where all these quantum riddles, they're clearly there. So the next thing we're trying to understand is how homogeneous and isotropic is this thing. That's also, of course, a hallmark of classical de Sitter. It looks the same everywhere in all directions. So in what sense can we invent a quantitative measure, an observable, that tells me how homogeneous and isotropic this, quantum fluctuating de Sitter candidate is? So that's what we are currently developing. And we're looking at inhomogeneities. What are two-point functions? It is a bit technical, but this is things that one might be able actually to relate to what people do in our universe cosmology, which of course is in a totally different language. Fixed background, QFT on a flat or curved background, and everything has to be perturbative. So there's a big gap, but we have already zoomed in on some objects that we believe, similar things can be computed, and if in the best of all worlds we compare. So the other day I was talking to someone from Quanta magazine, and he said at the end of the interview, Renate, you're so optimistic about quantum gravity. Everyone else I've talked to seems very downbeat. And I said, look, I have a good story. I know exactly what I'm going to do in the next few years. So on this point, I'd like to end and thank you very much for all your attention.